Hey everybody, welcome to Question Barn. So today we're going to answer a question, and we're going to answer a question with Ken. Hey Ken.
Hey Ben, how's it going?
It's going good.
Excellent.
What's new with you?
Not much. Done the term this year, which is good. And so now it's summer, and time for research to happen.
Hey, your university, the sessionals and TAs are on strike. Is that still going on?
The TAs finished their strike just before the end of the term, so they were out for about a month or so.
Did the university cave into their demands?
They went to binding arbitration in the end, so I think both sides kind of gave some ground.
I see. Well, as long as they're happy.
Yes. I guess they're happy. I hope they're happy. Hope they get what they wanted.
Yeah. I'm in the middle of writing exams, writing them, not being tested on them. I'm like,
right.
I'm taking
creating exams.
Yeah, I'm taking a break to write the physics exam that I'm going to ask my class to do in a couple days. I don't know.
You haven't had exams yet?
We're in the middle of exam period.
Oh, okay.
Yeah. But I visited the University of Calgary recently, and they were still in their term up until the end of this week, I think.
Wow.
Yeah.
It's amazing how different these schedules are.
I know, right? Jeepers creepers.
Crazy.
All right. Today's question is by a guy named Ramiro, and he asks, hey, I've heard that bosons are the force carriers, so what force is the Higgs boson, quote-unquote, carrying? What do you think, Ken?
This is an excellent question that is a source of much confusion, I think. Good job, Ramiro. This is a good one. So are we going to go ahead and try to answer this?
Yeah, you take the lead, Ken.
So I think what we have to do is define what force carriers actually are. So when you think of forces and the way that particles interact with forces, like for example, you take like the electromagnetic force, right? You think of how particles interact with the electromagnetic force. It's much like Ramiro is suggesting. The force carrier for the electromagnetic force is photons, right? They could be virtual photons, but photons nonetheless. So when you have an electromagnetic interaction, the particles exchange photons. Everybody's happy. That's how the force gets transmitted.
Well, here, pause. Let's pause the phone and take it back a step, because you're right. I mean, so this is how particle physicists talk about forces,
right?
So what happens is there's an electromagnetic field, right?
Yes,
and so that's.
But I was trying to avoid saying field.
Well, what's wrong?
Because what we just between you and I, what I think we need to do is go into the Higgs field and how that's different from the way that electromagnetic fields interact.
Okay. Well,
because what I would say is that there's the what we think of, like what everybody talks about when they talk about the Higgs, is they talk about the Higgs field, right? As a particle moves through it, it creates kind of a drag. I mean, that's the analogy that most people use, which gives particles mass. Right? But the Higgs boson is not really the exchange particle for the Higgs field. Particles interact themselves with the Higgs field, and the Higgs boson is a manifestation of the Higgs field. It's a result of the Higgs field. It's an excitation of the Higgs field, not a particle in the same way that we would think of the the photon as the carrier of the electromagnetic field. At least that's the way I would explain it. Maybe that's not the best way.
Well, okay. Keep going the way you were going before. Don't mind my interruption. And I'll leave this whole thing in, and then people will hear us metal talk, and they'll be like, "Wow, meta talking."
Right. So as I was explaining the photons mediate the electromagnetic force, but I think the way that the Higgs works is different. The Higgs, and what was found as the Higgs, is really an excitation of the Higgs field. So when they talk about the Higgs boson, it is a boson in that it's associated with the Higgs field, but it's not a carrier in the way that you would think of carriers with the other forces. If, for example, the weak force uses the W or the Z particles, those are just heavy bosons. But the Higgs field essentially has an excitation, which is the Higgs boson, which I just realized this is getting super complicated.
Yeah.
There's got to be a way to...
Okay.
Go on, yeah.
Here's what I would say. I would say, so back in high school you learn about the electric... So, everybody's qualifying this in terms of the electromagnetic field, and that's a great example because we're used to talking about photons.
Exactly, yeah.
Which are, people use photons in two different ways, right? I mean, so there are the literal light is coming from the sun in the form of photons. Right?
That's true, yeah.
And then there's the other one where we talk about, so people talk about the electric field pushing charges around, or the magnetic field pushing charges around. And when we quantize the electromagnetic field, we end up with saying, well, all these waves, all these pushes turn to particles, and these quantum objects, the quanta of pushing is essentially is a photon, right?
Yes.
So we talk about the interactions in terms not of forces, but in terms of little boops of information being exchanged in the form of these photons.
That's correct.
Right. And those photons are what people call them virtual particles sometimes when they're doing the thing. They're not actually, well, I mean, people, it's complicated whether or not it's actually happening, but when people say a photon is going between two atoms and that causes them to push on each other, that's an approximation scheme, right?
That's right. I mean, it is similar to this in the way that if you have two electrons approaching each other and they push each other away as they get closer, you would normally see that drawn with a photon exchanged between them, right?
Right.
It's not like that photon actually existed. I mean, there wasn't a photon in the same way that the photon comes from the sun that was sent by one electron to the other electron.
Right.
So it's what's called a virtual photon.
Yeah, energy isn't necessarily being exchanged. So you can have two things that are interacting via these virtual photons, causing them to push against each other, like a positive and another positive charge. They might be sitting still pushing against each other. But in addition to that, there's no energy being exchanged. So, when we talk about light, we talk about photons. Those are little particles of energy coming out from the sun, massless, moving at the speed of light. When we talk about photons in the force sense, we're trying to calculate the force, and we're doing it in terms of a infrastructure where we describe force in terms of the exchange of particles. And before I say, I've been saying the word approximation a lot. It's a remarkably successful way of describing interactions.
It describes all the interactions as we can test them right now. It's a very good description.
That's right. We're quantizing it when we talk about these virtual bosons being exchanged. It's an approximation, but we're essentially quantizing the force between the two. So to the Higgs boson. So there's a Higgs field, and everything's kind of interacting with it the same way a particle with charge will interact with the electromagnetic field, right? The more charge you have, the more you interact with it. Similarly, things interact with this Higgs field, and that's nice. And so you can talk about stuff mediating. But the Higgs boson, the thing that they discovered at CERN, is kind of like it's not a virtual particle. It's a real particle, like the photons coming from the sun are real particles. This was an actual excitation in the Higgs field. So it's a particle in the Higgs fields floating around, just the way a photon is a particle of light flying towards us or whatever.
Yeah, and I think the differentiation starts to become, for example, the Higgs boson, when you talk about the other bosons, they are incredibly long-lived in comparison to the Higgs boson. The Higgs boson lasts for like 10 to the minus 22 seconds or something like that. It's incredibly short-lived. So it's a different type than the other bosons, but it is still a boson. It's still an excitation of a field, basically.
You know how physicists often will derive their own units of measure in terms of usefulness, right? So people sometimes talk about the Planck length as a distance, or they talk about barns as a unit.
I was going to say, just like your bunny.
Yeah, right. So there should be one called the quit, which is a unit of time, and it's 10 to the minus 20. Seconds, and it's the amount of time before the student who never comes to class in first year physics sits down at his exam and then gives up.
Right. That's a very short time, yes.
So the Higgs boson lasts even shorter than that.
Yeah, it's like 0.01 quits.
Yeah.
Yeah, it's very short-lived. Well, but I mean, and when you talk about the particle this way, it makes it a little bit easier to understand kind of what happened at CERN, right? They essentially took a lot of energy, they smashed things around, and eventually they excited the Higgs field enough to create this boson, which lasted for a fraction of a quit and then decayed, and that's what they saw. So I mean, it's like it all hangs together when you talk about that kind of thing, right?
Yeah,
Which makes it so cool.
it does.
But then you start to talk about what force is actually being mediated, and that's a little more complex. It's a great question.
Yeah, can two objects push on each other using the Higgs field?
Good question. I don't think so. I think each particle interacts individually with the field, right? And interacts on its own with the field.
Right.
I mean, I'm going to fall back on being a particle physicist, which I sometimes pretend to be, and say if I were to draw the Feynman diagram for this, it's a particle interacting with the field. So you can't have the field as an intermediate between the interactions of two particles.
Oh, right. There's that thing where you say, "Oh no, you could make." So when we talk about like the weak force, historically there was a big fancy calculation someone did. I think it was like Yukawa, one of the Japanese guys, and he said that so the Higgs is a really short-lived force. Like it doesn't spread out over a large distance, not like gravity or electromagnetism.
True. Yeah.
And he attributed this to the force-carrying particle, so the virtual particle having a mass. So the gravitational gravity, when you quantize it, quote unquote, they say it's a massless force-carrying particle. Electromagnetic waves, photons, also massless, and so.
What about the weak force?
Yeah, so the
W and the
force,
Z have mass.
That's right. They have mass because they're short-lived particles.
They are. That is true.
Right. So it's a virtual particle, and it can. So people, the picture they paint, they say it can pop into existence, but if it does, it needs to obey the Heisenberg uncertainty principle, right?
Right.
And so the energy of something doesn't work well with time, the same way distance and momentum, or position and momentum, don't work together. Time and energy don't work together. So you're allowed to fudge how much energy something has, but only within a small time window.
Yeah, so for example, you can violate energy conservation, but the more you do it, the shorter it has to be.
Yeah.
The shorter it can be, the shorter you can violate it for.
Right. So the particle picture for how the weak interaction works is they make these WZ particles with mass, and that means they can only exist for a short period of time before they disappear, don't have any effect, right?
That's true.
So the deal is if you're emitting these particles because you're trying to interact with something else using the weak field, the particle will decay. If you're trying to interact with something that's too far away, your force-carrying bosons will decay before they reach the destination.
Yeah. So I think that's So I think that comes back to you can have particles interact themselves with the field, but you can't use it between because any distance would be too far. Any time is too long, essentially.
Well, yeah. So in this case, the mass of the particle dictates how far away from the particle the force will, how far away the emitting how far away from the emitting particle the force will be felt, right? And so they can interact through the weak field just at very short distances. And so if you're going to do the same thing with the Higgs field, it would need to be very, 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 very short distances because the boson's so heavy that it would, the time scale that you would need to be for the universe to allow one to fudge a virtual force-carrying boson to fudge into existence and out of existence would be really small.
Yeah, but I mean, yes, I agree with everything you're saying. I just think, the scales of mass for the W and Z are not so far from the Higgs, right? The Higgs about 1.5 times, right? The W and the Z are around 80 GeV, and the Higgs is 126 or whatever CERN said, 125, 126, something like that. So they're not ridiculously different scales.
Oh, I don't know. That's a good question that I don't know the answer to. Because
Yeah, so I think the W is 80 and the Z is 91 GeV, and I think the Higgs is 126, something like that.
So if they were interacting with so that's on the on the scale of inside of a nucleon.
Yes.
Right?
So I'm not disagreeing with your description. I think your description is right. I just wanted to say, I mean, it's not like the Higgs is an order of magnitude heavier than the W or the Z. They're in the same ballpark.
But so associated with these masses is a distance scale, right? Because
That's right.
There's a time
Absolutely.
scale, right? And so the weak force things can only interact through the weak force in the width of a nucleus, right?
Yeah, and the Higgs therefore is 75% of that or something.
So we would have nucleons interacting with the Higgs force if they could. I don't know the answer to this, Ken.
Yeah, I fall back on. I don't think they can, but I'm not 100% sure.
Well, that's super weird.
That's a very interesting question, actually.
Because it's a scalar field, and scalar fields are wonderful because they're simple.
Scalar fields are good. Yeah, all of that is really good. So why don't you get Higgs Higgs mediating interactions between particles?
Because we could observe that we smash nuclei together all the time.
Sure.
We're fairly familiar with the. I don't know.
As a species, we are very good at smashing things together. we have proven this time and time again.
Well, anyway, I think that's probably as far as we can go on this particular topic, huh?
Well, it's kind of unsatisfying in some way, because I'm not actually sure.
I think we answered the question as well as anybody could. I hope
we answered the question. Ramiro, out there, I hope we answered your question.
Sorry, Ramiro. Part of the answers to your question involve very, very high-level physics, but we did our best.
Yeah, and then, the problem is that you start to talk about the Higgs and, symmetry breaking, and then it gets really confusing at some point.
Yeah. Well, anyway, that's it for today's episode. Thanks, Ken.
No problem, Ben.
All right. If you want to ask Barn the Bunny a question, ask the question Barn a question, send me an email at TIPHYTER, that's TIE Fighter, at titaniumphysics.com. And we'll put it on the pile, and then we'll record one whenever we have some free time. Okay, that's it. See you, everybody.